Hi, everybody. Welcome to the next talk in the test and validation track. Myself, Anna Mathew, and with me is my team member, Tommy Yan. We're both from Microsoft. And the talk is on primarily on the design for debug thinking and a perspective of the same from the hyperscaler view of it with respect to bringing AI systems to the market fast and with high level of stability. So the whole problem statement here is AI GPU server systems, as we all know, are very complex and very powerful components in the modern data center. With the PCIe subsystem serving as a key example of the same, it alludes to the fact that there's a number of integration issues that you see stitching the whole system together. Primarily because we use different manufacturers all the way from the CPU to the retimers, the switches, and the accelerator cards. And having to stitch all these different components together has hindered the debuggability, and it makes it more challenging for us to diagnose and resolve issues, thereby impacting the overall stability of the platform. As we move to the second slide, we'll be talking about the current state of art and also in detail cherry-picking 3 case studies in this space to show the complexity of the debug that today we have to deal with as we navigate this solution.
Okay, thank you, Anna. So, here I shared some practice of our current shipping products. You can see from the diagram, it's heavy complex PCIe connection there on the AI GPU system. From the CPU, through the retimer to the host interface board. And there you'll find the PCIe switch and connect it all the way down to the GPU baseboard. And there you have another retimer. And then finally, through this long pole path, you reach the GPU. So now I want to share some basic things to get started and what we learned in the last this generation of the debug. So we do the test, release, and the debug for these AI systems in Microsoft. So I'll start with that. The point 2 is to basically to pre-align with each individual component owner, companies, and expertise, what logs we want to collect and how when we run into different problems. So for example, going from the bottom to the top, say we will talk with the GPU provider. What happens if the GPU is stuck? What log we need to collect and how? And then I will go to the go up to the retimer side. I'll ask the same question: what kind of debuggability the retimer have? Which plays a key role in this complex PCIe environment. Not only to itself, the retimer itself, log is important, but it also serves as the key debug components facilitation for the GPU as well. So we need to ask that question: what kind of debuggability you can provide when I have to isolate the problem with the retimer and GPU? And the same question going back and forth to the PCIe switch, to the CPU board retimer, and to the CPU. And not only in the normal case, which you can typically collect logs from the in-band, but also we need to consider the situation that, for example, the system is hanging there, so you cannot do anything with the in-band. So if that happens, we need either from the out-of-band way from the Redfish or the BMC or the SMC, or through the hardware debugger. We need to collect the necessary logs in order to move forward. Or some silicon provide the automatically crash dump or postcode. Those kind of debuggability mechanism will help us move forward to identify the root cause. Now, going to the point one is to, when the issue happen, when we run into the various of problem, really, the experience was we have to find some way to accelerate the issue's reproduction for the quicker logs collection and to prove different hypotheses and the debug drops. And another way is we need to, as the test engineer to swap hardware and firmware around to really see which piece is playing the key, affecting the results. And then the third point here is to really, from different source of the logs, you can see this is a very complex system, right? So you get the logs from different source, correlate them together by even combining them to the same or similar timestamp, and then analyze the logs together, and then adjust the firmware debug builds as needed to drive those to reproduce and drive the conclusion for where the problem. Yep. So next, I'll go to share a few examples that we studied in the last generation. So this is a PCIe problem we ran into several times. So what we see is the PCIe switch downstream port. We see a surprise link down. And sometimes we see the switch was only trained at Gen 1. It's lost the downstream devices. So that is a boot time problem. So what we did is we gathered different expertise together, and instead of doing continuous power cycle, which can take 30 minutes or even longer, so we kind of speed up this process by running the PCIe LTSSM loops, and try to use that to reproduce the problem much quicker. And also we try to, in the case we run into, we switch the hardware and firmware around, and we didn't see it follows the specific hardware or firmware. And now we are coming to the log collection part. So what we see is so when the issue happened, the OS was hanging. So in order to collect the necessary logs from both the PCIe switch and the GPU baseboard retimer side, we had to change some settings to let the OS continue to boot. Because at the beginning, we use the hardware debugger from the PCIe switch. And it's very time consuming and not easy to set up. So we change some settings so that we can allow the operating system continue to boot, even we see the PCIe surprise link down. And by doing that, we also needed some modified retimer firmware so that it will kind of stop on fail. Because the retimer has like the retry or recovery mechanism, it only can save like handful or 2 digits LTSSM states. So we have to get some customized retimer firmware in order we can do not do the retry. So we can collect the necessary logs with the limited number of the PCIe training states. Yeah, so by doing that, we were able to collect the necessary logs from the PCIe switch and the retimers, and with the expertise there, so we narrowed down the problem with the PCIe training stage. It's the equalization timeout. It's yeah, handshake timing kind of a problem. So eventually, with multiple rounds of the retimers and the switch firmware updates, we got this issue resolved. So that's the first case. The second case was also a PCIe related problem. So in our data center, we see the PCIe switch run into the completion timeout problem. It's only happened when our data center PCIe workflow, including involving the device resets and also some tools, special PCIe switch address access. So it's not following the hardware or firmware, but it's on our data center. So our team and other team have to spend a lot of effort trying to reproduce it, with that special setup. So at the time we have a data center lab, so we were able to hook up a PCIe switch hardware debugger, and we find by looking at the CPU, this problem happened on the upper piece. So we look at the CPU logs and also the retimer logs. We didn't find abnormal. We didn't find abnormal PCIe problem. But when we get the PCIe switch logs, we find actually the switch firmware was stucking. It's confirmed by the switch firmware dump and by the switch provider. So after that, our focus moved to the switch firmware side, the PCIe switch firmware side. So eventually by changing, basically do not allow access to some certain sensitive address range, this issue was resolved. And the third case is related with the logs correlation. So it happened when we see a few GPUs completely missing at the boot time. And by looking at again PCIe logs, we didn't find any abnormal there. At that time, the team started to suspect some power on, power sequence problem, and even use the scope and capture the key signals upon the failure time. But still, we didn't see any abnormal, but we noticed in the point 1 that this issue happened after a firmware updates, which significantly kind of delayed the GPU subsystem boot up time. So at that time, we started to log in the BMC and the XMC, start to look at their logs. And from the XMC log, we noticed the signal it should receive and send was the result was correctly. It behaves correctly. But from the SMC, from the BMC's log, by looking at the timestamp and comparing with the SMC's correlate time together, we find the power button actually was pressed way earlier. It should get some special FPGA ready signal from the UBB chassis before it can really turn the power button on. But actually, it's turned that on much quicker than that. So as a result, the host already started to power on and do the PCIe enumerations and trainings, even when the GPU side was not ready. Yeah, so here is an example that the correlating the different timestamp, the component timestamp, was critical to try to isolate a complex system like this. Okay, Anna.
So to summarize those 3 case studies, right? So we have four key items we have highlighted here. One is the hardware debugger, right? With respect to the retimers or the switches, we always have to choose and learn each time around, the new utilities and such, right? So we need to have some standardization that could be used across vendors, which makes the log collection swift and avoids prolonged delays. The second piece is about debugger log collection, right, by customers and partners. So the logs that we collect are all, obviously they are PCIe related logs, but there's no standard format for decoding these logs, and some are customer proprietary as well. So the learning here is how can hyperscalers use this more effectively and download potentially these binary logs and decode it to a certain extent to do certain amount of assessment and analysis prior to actually involving multi-party, right, so that the debug can move faster. The third piece is all about PCIe analyzer connectivity, right? As we move to more and more complex systems, if we don't have a direct PCIe analyzer connectivity to these endpoints, it can limit us from collecting the required data at the point of failure. And also, if we have a intercept on the trace, that could lead to some signal changes, right? So how do we do this more smarter as we move to more complex systems, right? So it's ensuring ability to connect a PCIe analyzer to provide comprehensive analysis while not disrupting the end-to-end path. The fourth and the final one is about streamlined security exceptions for remote debugging, right? So how do we implement a process across the industry with respect to security exceptions potentially for non-production hardware to make remote debugging more effective? Currently the process requires a lot of special steps with respect to unlock firmware and other nuances, right? So this is an area also that generally impedes us from moving fast when we want to look at data across this different ingredients. So moving on to the call of action. Let's design AI GPU systems with better design for debug in it so that it makes it easier for us to debug. How can the industry help us here? Definitely OCP has the Test and Validation Enablement Initiative that could be a great forum to bring in some of these ideas and collaborate across the board to bring those to fruition. Joining the new Open Systems for AI initiative is another space where this could be brought up. And for additional information on the ongoing efforts in this space, definitely please check out the Open Compute project. Thank you.
Any questions?
A lot in the ability to replicate the problem in a lab for doing debug. Our experience has been that some of the problems you can only observe in the field. So how do you trade that off for problems that are related to marginality and things like that?
For the field or in the data center?
Yeah, field, data center.
Data center. Yeah, we have a data center team. I mean, we rely on the RAS and the logs collections on the data centers. The GPU have some capability of doing, like I mentioned, the postcode and some, self-dump when they see the problem. And on the PCIe, like retimer and the switch side, particularly this retimer have some auto-ban mechanism that we can dump the key statics, like the signal integrity and the LTSSM training states in the data center. And when the issue happens, we can also use the in-band to put that node in out of service and run some diagnostic that way. Yeah.
Yeah, like if you want to get more details, OCP accelerator RAS requirement document is like provided a lot of requirements around debug collection at the time of crash, because very hard to reproduce the issues. We want to collect at the top. It also talks about analyzer tool requirements, because there are security requirements to integrate it to hyperscale infrastructure. That spec will be available in next week. Okay, you can look in that.
Thank you, Rama. This is part of the hardware management OCP work group, right? Thank you. Any other questions?